Good morning, everyone.
Morning.
Can you see my screen?
Yes, I can.
Good. So today we continue our discussion about matrix analysis of truss structures. And before I continue, I go for a quick recap because we just did one example, but we didn't finish it last week. So, okay. We are really implementing this matrix. And for implementing this matrix, we need 5 parameters, A, E, L, and lambda X and lambda Y. So A, E, L is really the characteristics of each element. And lambda X and lambda Y can be defined like this. It is just coming from the coordination of the points at the end and beginning of different elements. So we write this stiffness matrix for individual elements separately and then try to assemble the whole structure stiffness matrix by putting these individual stiffness matrices into the right places in the bigger matrix. So just to go through the first example again, just to recap, bearing in your mind that we are just going to calculate lambda x and lambda y for every individual element and putting those values into this 4x4 matrix. And then we will assemble the whole structure matrix. So as you see here, we have only 2 elements, and it's a very simple truss structure. So first of all, we need to define the coordination system. As you see, the coordination system is X and Y. So every coordination location for points will be expressed in this Cartesian coordination system. So the origin is here, just here. The intersection of these 2 elements is the origin of the coordination system. And for the first task, I need to number the joints I have. So I have joint number 1, joint number 2, and joint number 3. These are shown by the circles, so they are the joints. When you distinguish your joints, you need to number your elements. So this is element 1, which connects joint 2 to 3. So this arrow here shows that the element number 1 connects joint 2 to 3, and the 2 is called near end and 3 is called far end. So the beginning of the element is near end and the end of the element is called far end. It's like I'm standing beside the beginning of the element, just beside joint 2. I'm seeing joint 2 beside myself, and I'm seeing joint 3 far away from myself. So we have always a near end and a far end. So for element number 2, I just name it element number 2. The near end is, see the arrow key here, arrow here. The near end is joint 2 and the far end is joint 1. So when you know the near end and the far end joints, you can go to lambda x and lambda y and just calculate the difference of the x coordinations for the far end and near end y coordinations from far end and near end. So over divided by the L, obviously. So for example, for element number 1, this is the x far end, and this is the x near end, aren't they? See, for element number 1, the near end is joint 2. Sorry, the far end. The far end is joint 3. So x for far end is 3 meter. It's 3 meter. The origin is here. And x for near end, which is joint 2, is 0, which is just here. So over 3 meter, which is the length of the element. Again, for lambda y, it is, although they are both 0, but lambda y speaks about y for the far end, and this is y for the near end, aren't they? So for the far end, the y is 0, and for the near end, the y is 0. Y-axis is this one. So the 0 is here, positive values and negative values. So every horizontal line here have all the points with y coordination equal to 0. So if we have lambda x and lambda y, we just put, again, the previous slide, I just put the lambda x, lambda y for each element into this matrix. So for element number 1, I have the K1 matrix, which is 4 by 4. Before continuing, I'm just going to emphasize that we need to understand about the degrees of freedoms as well. For the truss structures, for each point, for planar truss structures, for each point we have 2 degrees of freedoms, which are translational deformation in x and y. But you will see for beam structures or for frame structures, which we have theta, the rotational deformation. In that case, every joint has 3 degrees of freedom, 2 translational and 1 rotational. And but for now, for the truss structures, we don't have any rotational deformation. We only have, for each point, we have delta x and delta y. Each point, each node can go in the x direction, can deform in the x direction or in the y direction. So when we have a truss like this, and for this stage, just forget about the supports. We will take the supports into consideration later. For this example, we have 3 nodes. So if we have 3 nodes, each node has 2 degrees of freedom. Altogether, we have 2 multiplied by 3, which means 6 degrees of freedom, right? So the best way is to write those degrees of freedoms clearly on your structure. For example, if I use another color like green, maybe. Okay, so it's really depends on you. You need to number the nodes, number the elements, and number the degrees of freedoms. Okay, so the sequence is up to you, doesn't matter. But when you define your degrees of freedom, just follow them. Okay, so we did this last week with delta 1x, delta 1, 2, but today we are going to use another way of defining the degrees of freedoms, but both work in the same way. So last week I wanted just to be more clear. Now we can just simply number them in a very simple manner. So this is 1. Translational deformation of node 2 in the x direction. You can name it delta 2x. That's fine if you like. this is number 2, the degrees of freedom number 2, which is sort of delta 2y. This is number 3, the degrees of freedom number 3, which is delta 3x. This is number 4, which is delta 3y. Either use delta 3y, for example, or use 1, 2, 3, 4, 5, 6. So this degrees of freedom is number 5, but you can name it as well as delta 1x, because this is x. And this is number 6, which you can either use the notation delta 1y, right? So altogether we have 6 degrees of freedoms, right? Uh, Before I continue, if anybody has any question, just raise your hand and I will see that you have a question. I will stop and give the floor to you to ask your question. If you take a look at the top of your Teams, there is an icon named reactions. If you press on that, the first one from the left is raise hand. So if you press that, I will see a raised hand in front of your name, and I will stop and give the stage to you to ask a question. Don't hesitate to stop me and ask a question. That's fine. Whenever you have some doubts, just do it. So we have all together. So uh, don't forget, we define the coordination system, we number the nodes, we number the elements, we number the degrees of freedoms. If you do those, it's very simple to assemble these kind of matrices. So K1 is assembled by knowing lambda x and lambda y and A, E, L, and L. So, but before proceeding to the element number 2, we need to write these kind of notation as a hint for ourselves. They are not numbers inside the matrix. They are just some hints for myself to better understand what kind of matrix this is for. For example, because this is K1 and K1 is a 4 by 4 matrix for element number 1, and element number 1 is connecting node 2 to node 3. So start with the near end. It's element number 1 is connecting node 2 to node 3. So node 2 is the near end, which has degrees of freedoms 1, 2. See, 1 is here, 2 is here. And the far end node, node number 3, has degrees of freedom 3 and 4. So 3 and 4. So I just copied 1, 2, 3, 4 here as a column just to have them as a hint for myself for later on. But always for these kind of 4 by 4 stiffness matrices, you write delta x and delta y for the near end and delta x and delta y for the far end. If you're using 1, 2, 3, 4, just put 1, 2, 3, 4. If you're putting delta 2x, delta 2y, delta 3x, delta 3y, as I did last week, for example. It's just a notation, nothing more. So I know with this kind of hint, I know that every single number value inside this matrix is corresponding to a certain degree of freedom. For example, this 0.333 corresponds to the degree of freedom 1 and 1, right? So just repeat this for all the elements you have in your structure. Since I have only 2 elements, this is for element number 1, and this is for element number 2. For element number 2, I just calculate lambda x and lambda y again. You just need to take a look at element number 2, which is here. The arrow is like this, which means node number 2 is near node. near end, and node number 1 is far end. So for the near end, node number 2, you need to write xf minus xn, which are 3 minus 0. And for lambda y, you need to write yf minus yn, uh, which means y in node 1 minus y in the node 2. So far end minus near end. So if you calculate lambda x and lambda y, you can just put it in the formula, in this formula, and come up with the K2, the 4x4 stiffness matrix for element number 2. Just to have the hints on the matrix, I need to put these hints for myself. How I do that, the first two are for the near end, which is number 2, node number 2. So it's 1 and 2. You can either use the notation delta 2x, delta 2y. And the two remaining here will stand for the degrees of freedom for the far end, which is node number 1. So it's the degrees of freedom 5 and 6, or you can say delta 1x and delta 1y. Again, I have 1, 2, 5, 6. I just copy them here just to have the degrees of freedoms on my columns and my rows. And then when you finish with assembling these kind of 4x4 stiffness matrix for different elements, you need to put individual 4x4 matrices into the bigger matrix for the whole structure. And for the whole structure, this is the stiffness matrix for the whole structure. And for the whole structure, you just remember that how many degrees of freedoms you have. So I have 3 nodes multiplied by 2, which means 6 degrees of freedom. I just write a 6 by 6 matrix full of zeros and try to replace the K1 and K2 matrices into the right place. For example, for this number, you need to put every number into the bigger matrix. For this number, 0.333, you need to put this number in the column 1 and row 1 in the bigger matrix. So here is the bigger matrix. So this is column 1 and this is row 1. This number 0.333 goes here, right? But it is 0.40 something. Why that's different? Because I have still when I finish with the first matrix K1, if I go to the next matrix to put them in the bigger matrix, I have another number here which corresponds to column 1 and row 1. So this number goes to this place and will be added to the previous number 0.333, and you will get 0.4. So for example, let's say this number minus 0.128. You need to do it for all the numbers. I mean, it's not arbitrary. You start with the first number, you will do for all the numbers, we'll put all the numbers into the bigger matrix. So for this number, it's going to column 2 and row 6. So column 2 is here, row 6 is here. So it is here, as you see. So every single number from the individual matrices go in the right places in the bigger matrix. So with this approach, if you put all the numbers from this matrix and this matrix into the right places in this matrix, you will get the whole structure stiffness matrix, which is a kind of 6 by 6 matrix. And this is really the most important part in solving a problem with stiffness with matrix analysis. So if you have this matrix, you just can simply write this is my K matrix, and this is the vector of delta, and this is the vector of F. So F equal to K multiplied by delta, which is the famous relationship for the simple spring, as I told you as well. So in this case, this 6 by 6 K matrix is coming just from the previous slide when we assembled it with putting those K1 and K2 into the bigger matrix. And the delta, and the delta is just the deformation of, let's say, the, the deformation of different degrees of freedom. So I have 1, 2, 3, 4, 5, 6 as the degrees of freedoms. So for the deformation, I have D1, D2, D3, 4, 5, 6. And I know that D3, 4, 5, 6 are 0 because of the supports. I have two simple supports here, which makes D3, 4, 5, 6 0, and I only have D1 and D2. They are free to move, and they are corresponding to node number 2. So this is node number 2, and the degrees of freedom number 1 and 2 are free to move. On the other hand, this is the left one is the force matrix, force vector, or better saying external force vector. And we know that along with the degrees of freedoms 1 and 2, we have 0 and -2 kilonewton as external forces. These are external forces applied on joint 2, and these are the support reactions which are unknown. And it's always the case that wherever we have external forces like this, the degrees of freedoms are free to move. And wherever we have support reactions, the deformation corresponding to them are 0. So we can just go through dividing this bigger matrix into 4 parts, or better saying that um, I'm sort of when we have a vector equal to a matrix multiplied by a vector, I can say that this 0 is equal to this line multiplied by this column. And this 2 kilonewton is equal to the second line multiplied by this column. So if you do that, you will have two equations. And if you come back and write them again into the matrix form, you will come up with this kind of simpler arrangement of the matrix. And this kind of process means that just to have a very simple rule to do that is wherever you have the support displacements equal to 0, which means in this case I have row 4, 5, row 3, 4, 5, 6. Okay, if I have this 0 here in row 3 or in the third uh, degrees of freedom, just go and delete the row number 3 and column number 3. And for the fourth one, fifth one, and sixth one, do that. So 3, 4, 5, 6 are 0. So I eliminate on the lines 3, 4, 5, 6 and the columns 3, 4, 5, 6. If you do that, you will see that only this part will be remaining. All of these will be gone. So these 0, 2 will be equal to this part times D1, D2, which is this one. This is nothing. And this is called the implementation of support conditions or boundary conditions. With this kind of implementation, somehow I've applied the mathematical definition of the supports, and now my mathematical formulation understands that I have two supports, and that's why the structure is now stable in the mathematical form. And if you try to inverse this remaining stiffness matrix, the matrix is reversible. Otherwise, if you try to reverse the bigger matrix, the 6 by 6 matrix, it's not reversible, and you will come up with a determinant equal to 0 or negative, and it means that it doesn't have any support, and it should be like that. So if you just solve this 2 by 2 equations, you will come up with D1 and D2 as the deformations in the X and Y directions in joint 2, and which means they are corresponding to the degrees of freedom 1 and 2, as you see here. This is degrees of freedom 1 and 2. When we come up with this point, we have solved our problem in terms of deformations, and the only remaining part would be to obtain the support reactions and the internal forces in each element. Otherwise, we don't need anything else. We cannot expect anything else. So we're really looking for the deformation of the structure, the internal forces, and the support reactions. If you have all of these three types of outputs, you can say I have got all possible analysis outputs. So for support reactions, you need to use those lines that you have already eliminated here in the big matrix. So for example, just go for the third line. This Q3 is the third line times this column. So this is doing that one. And if you use those 4 lines that you were eliminated, you will come up with Q3, 4, 5, 6, and they are just the support reactions for 2 supports we have. And when you come up with this point, you have all the support reactions. And one beautiful thing you can do before going for the final part, which is obtaining the force elements in each element. So if you can somehow write the equilibrium equation for the whole structure and see if the equilibrium equation for the whole structure is valid, you haven't done any mistake in your calculation. Because when you come up with this point that you have all the support reactions, you can say, for example, for the whole structure, you can say summation of fx should be 0. So summation of fx is the support reaction in the degree of freedom 3 plus 5, and we don't have any external forces, should be 0. So take a look at here, 3 is minus 1.5, and this is plus 1.5, and the summation of these two numbers are 0 and should be 0. So the summation of fx equal to 0, which is one of the equilibrium equation, is verified. And also summation of fy, for example. Summation of fy should be whatever you get from the support reaction in the 6 and 4, and you have 2 kilonewton here, right? Pay attention to the direction of them. So whatever you get from 4 and 6 are here. 4 is 0 and 6 is 2 kilonewton in the upward direction, and you have a 2 kilonewton in downward direction. So they are in agreement together, which means summation Fy is equal to 0, which means the second equilibrium equation is verified. You can do the same for summation of m equal to 0, and you will see, for example, if you do that through the point, the node number 1, for that, number 6, 5, and 4 will cross this number 1. They are out of the game. you will have only number 3, which is minus 1.5 times this length, which is 4 meter, which you will get minus 6. And this is 2 kilonewton times 3 meter. You will get plus 6 kilonewton meter. And altogether, the third equilibrium equation is valid. So if you test or validate, verify your 3 equilibrium equations for the whole structure, when you come up with the support reactions, it's a second improvement that you it's not a second, it's a kind of improvement that you haven't done any numerical error in your calculation, so you can see that your calculation is valid. So as the last step, not least, we need to calculate the member forces, whatever forces we have in the different elements. For this purpose, we'll go back to the previous slide. This is equation 1423 from the book. Again, I don't go through the demonstration. Every element, and for the far end, the internal force is AE over L. You already have them. For every element, you have lambda x and lambda y. You have them. And dxy, dfxy, these four are the deformation for the near end and for the far end. You already have them. So if you implement this formula for every single element, you can simply get the internal forces for each element. So you only need the 5 parameters you used for assembling the stiffness matrix, 4x4 individual stiffness matrix, and the obtained final deformations in the beginning and end of each element. So, for example, for element number 1, which are we for element number 1, we have lambda x and lambda y and L and AE. So this is AE over L, and these 4 are lambda x, lambda y, and you see minus lambda x minus lambda y, and lambda x and lambda y. So minus 1, 0, 1, 0. And this is coming from this fact that element number 1 or member number 1 connects node 2 to 3. So near end is 2, far end is 3. So near end has the degrees of freedom 1 and 2. So these two are the deformations in 1 and 2, as you see, and these two are the deformations for 3 and 4, which are obviously 0 because of support. So these 4 are calculated here. This is 1 and 2, and we know that the 3 and 4 are 0. So if you add AE over L is a constant, and this is a kind of 1/4 vector, and this is a kind of 4/1 vector. So this is 1/4, and this is 4/1. The multiplication of two vectors like this, 1/4, 4/1, will be 1/1. So the final value for Q1 is a kind of scalar. It's just a number. It's not a matrix or vector. So if you multiply these together, you will come up with a minus 1.5 kilonewton as the internal force for element number 1. And if you do the same for element number 2, you will come up with 2.5 kilonewton for element number 2. And as you know, for truss structures, you only have one axial force inside the element, nothing more. So you only have either a tension or compression axial force in your element. So you don't have any shear, you don't have any bending moment. That's why you're just calculating Q1 and Q2 for your elements number 1 and 2. And with this step, you have already all the possible outputs from the analysis procedure. Uh, we just assemble the stiffness matrix. We just um, applied the boundary condition. We just solve the F equal to K delta, and we obtain the deformations in all the degrees of freedoms. Then we move to obtaining the support reactions, and then we try to come up with the internal forces in each element. So there is nothing really we can further do to solve any kind of other parameters for this structure. We usually always we have these kind of interests to obtain the deformations, internal forces, and support reactions. So before this is done for this example, and before we go to the next example, if there is any question, just go ahead and ask me. So I believe you all uh, are bearing with me and fully understood what we have done in this example. Good. We proceed to another example, which is this one. Um, First of all, we want to assemble the stiffness matrix. After that, we will put some external forces and we'll solve the problem. This is a kind of more complex truss structure. Again, it's a truss structure. And we have 6 different elements which form this structure. Uh, please pay attention that this is not a joint. These 2 elements just crossed beside each other and they haven't connected together. So we only have 4 joints. These are 4 joints, and the geometry says it's 10 meter for each length. And we have 2 supports. The top support, this one, is a simple support, and the bottom support is a kind of a roller support. So we all together have 3 support reactions, 2 for the upper support, top support, and 1 for the bottom support. So the reactions would be like this: 1 reaction here, 2 reactions here. So in terms of supports, this structure is determinate, but in terms of the different elements, it's not a determinate structure, it's an indeterminate structure. And you can test it with the formula we spoke in the beginning of the term as well. We can just give it a shot. 3j plus c equal to and 3m plus r equal. So how many joints I have? 3 times. I have really 4 joints, right? 4 plus. How many C I have? C comes from the joints, joint hinges. So I have 4 hinges. Every single hinge has 3 elements connecting together. So C will be equal to 2 for each node. I have 4 nodes. 4 multiplied by 2 is 8. which makes this one 20, right? 3m, how many members do I have? I have 6 members, right? 3 times 6 plus R is standing for reactions, which are 3. So it is 21. So the unknowns are 21 and the knowns are 20. The equations are 20. It means that I have one more extra unknown rather than the equation numbers I already have, which means this structure is a 1 degree indeterminate. And this is a good example to express that for the matrix analysis, for the directed stiffness analysis we are currently employing, it doesn't matter really if the structure is indeterminate or not. We do the same procedure for this, for solving this truss structure as we do if it's a determinative structure. And this is an advantage of this kind of approaches like directed stiffness method or matrix analysis we're implementing, because we don't have any hassle in terms of if the structure is indeterminate. We only follow the same procedure we just followed in the previous example. The only difference is that, for example, in the previous example, we had 2 elements. Here we have 6 elements. So you really need to repeat those kind of individual stiffness matrices which were 4 by 4 for every individual element. So you need to repeat that for 6 elements, for 6 different elements individually. You have for each element you have a 4 by 4 matrix, and we know that repeating something is very straightforward for machines, and computers are awesome in those kind of algorithms. So that's why this kind of approach is implemented in computer algorithms. So we start by assembling the individual matrices for each element, but before that, we know that we need to define a coordination system, then number the joints we have, then number the elements we have, and define the degrees of freedoms before going through the calculations. So as you see, this is coordination system, X and Y, and the origin is here. You are free to choose any other coordination system, and I strongly recommend all of you to repeat exactly this example by putting the coordination system somewhere else, wherever you like. Put the origin on point number 3, for example, or 4 or 2, or in the middle of the structure, and try to repeat all the steps to see what happens. Obviously, if you do that, when you assemble the stiffness matrix, 4 by 4 stiffness matrix for every individual element, the shape of your matrices and the numbers you will get inside your matrices will be different. But finally, when you solve the problem, the internal forces in each element will be the same as we are doing now, and the deformations will be the same, and the support reactions will be the same. So it's a very good practice if you try to uh, change the coordination system in this example, or even in the previous example, and try to repeat all the stages to see if you will get the same answers at the end or not. You should get. Uh, So after defining the coordination system, I need to number the joints. So as you know, we have 4 joints. So this is joint number 1, joint number 2, joint number 3, and joint number 4. So after that, we need to number the elements, which are element number 1, For each element, as you see, we put an arrow which shows the near end and the far end. So it goes from the near end to the far end. So for example, for element number 1, the near end is joint number 1 and the far end is joint number 2. For element number 2, it is arbitrary how to number them. It's up to you. For element number 2, the near end is number 1, joint number 1, and the far end is joint number 3. For element number 3, the near end is joint number 1, and the far end is joint number 4. And for element number 4, it's here. The near end is joint number 4, the far end is joint number 3. And the element number 5 connects the near end number 4 to the far end number 2. And the element number 6 connects the near end joint number 5 to the far end joint number 3. Sorry, I made a mistake. Uh, Element number 6 connects the near end joint number 2 to the far end joint number 3. See, this mistake that I already have done because we have too many numbers on the picture. And I strongly recommend you when you're doing this on a piece of paper, use different colors of pens. So, for example, have you place some convention for yourself. Like I use red for joints, blue for members, and another color for degrees of freedoms. With uh, uh, this kind of different colors, the likelihood of making mistake will be minimized somehow. So then when we for example, here I'm using red for joints, purple for elements, and green for degrees of freedoms. So this is uh, degree of freedom number 1, number 2, number 3, number 4, number 5, number 6, number 7, and number 8. I have 4 joints multiplied by 2, which means 8 degrees of freedoms. You are free to go if you want to name them, like, for example, uh, degrees of freedom number 1 and 2. You can name them like delta 1x and delta 1y. For example, 3 and 4, you can name them delta 4x and delta 4y. And for 7, 8, you can name them delta 3x, delta 3y. And for 2, you can name them, sorry, for 5 and 6 degrees of freedoms, you can name them delta 2x and delta 2y. It really depends on your taste, but if you name them like that, it's a longer name, but the benefit is that you're using the joints numbers into the degrees of freedom numbers, and you're avoiding from using any kind of new numbering for the degrees of freedoms. Maybe sometimes maybe it's better because the numbers of the degrees of freedom do not mix with the numbers of joints. So, but really depends on your taste. And as you see, the book author just used the simple numbering here. Uh, so we have defined coordination system. We number the joints, we number the elements, we number the degrees of freedoms. You need to do these 4 things before going through the real calculations. Uh, Anybody has any doubts so far? With numbering joints, elements, degrees of freedoms, and everything should be done in a single coordination system. With this definitions, now it's time to jump in to assembling uh, a single 4 by 4 matrix for every single element. So just to remember, I'm using this one again. So I'm going through assembling this 4 by 4 matrix for every single element. So I need to calculate lambda x and lambda y, and I know A, E, and L for every single element. Um, Again, I recommend you that if you have too many elements, like here you have 6 elements, you can make a kind of table for yourself in which the rows will represent the different elements and the columns will represent different characteristics for each element. We gave it a shot last week with Excel, if you remember. If you use that kind of Excel spreadsheet, it helps really just not to mix up the properties of different elements together. But if you do want to individually do that, still it's okay, and you need just to repeat everything for 6 times by calculating lambda x and lambda y. As you know, lambda x and lambda y are easy to calculate and put it in the 4 by 4 stiffness matrix. And we are just following the simple formula. The only trick you need to be careful about is for every single 4 by 4 matrix, just to write the top hint for myself. And the first two, for example, this is for K1. K1 is for element number 1, which connects node number 1 to 2. So the near end is node number 1, which has degrees of freedom 1 and 2. So 1 and 2 goes here. These two are for the near end, and these two are for the far end. So the far end is joint number 2, which corresponds to degrees of freedom 6 and 5. 6 and 5. So it's not 5 and 6. It's important. Be careful. Uh, for the first two, it is, for example, if you were using the notation like delta 1x and delta 2x, delta 1y, you should write, for example, here, the near end is joint number 1. You should write delta 1x, delta 1y, and for 6 and 5, which corresponds to joint number 2, you should write delta 2x and delta 2y, for example. So for every single 4 by 4 stiffness matrix, you need to write the first two goes for the near end, and the second two goes for the far end. And for both of them, you need to write the degrees of freedoms in the x and y directions. So you need to repeat it for member number 2, member number 3, and as you see, you will see in the next slide, member number 4, 5, 6. And for every individual member, you will have, for example, K2. K2, let's see together. K2 is for element number 2. Element number 2 is here, connecting joint number 1. So degrees of freedom 1 and 2 here. And far end is joint number 3. Degrees of freedom 7 and 8 is for joint number 3. For example, if we go to member number 4, again, lambda x, lambda y, and number 4 is here. This is element number 4, connecting joint number 4 to joint number 3. So the near end is joint number 4, which gives me degrees of freedom 3 and 4. And the far end is joint number 3, which gives me degrees of freedom 7 and 8, right? So um, let's do it for element number 5 as well. Element number 5 is this one. The near end is joint number 4, gives me 3 and 4. And the far end is joint number 2, which gives me 6 and 5. And the last element is element number 6, which gives me, where is this element? Element is here, connects node 2 to node 3. So the near end is node 2, which gives me 6 and 5 as the degrees of freedoms. And the far end is node 3, which gives me 7 and 8 as the degrees of freedoms. So we have all together 6 elements. Each element has a 4 by 4 matrix. So you have 6 individual 4 by 4 matrices, and you need to put all of these matrices into the bigger matrix, which is the matrix for the whole structure. The matrix for the whole structure, the matrix for the whole structure is shown here. And you need to really write an 8 by 8 matrix full of 0, okay? Why an 8 by 8? Because I have 8 degrees of freedom altogether. I have 4 joints multiplied by 2 degrees of freedom for each joint, which means 8 by 8, 8 degrees of freedom. So always the whole structure matrix is, the dimension is equal to the number of the whole degrees of freedoms. Because I have 8 degrees of freedoms, I need a big matrix, 8 by 8, full of zeros. So you need to put every single number you have obtained in those individual 4 by 4 matrices into the bigger matrix. For example, be careful about A and I. Okay, A and I is the same for all the elements, so it can go out of the matrix, but L is different, but I already have implemented them. So for example, let's say one of these. For example, minus zero point 0.1, where does it go? It goes to the column 7 and row, this is column 7, this is row 3. So this is row 3 and this is column 7. This should go here, as you see. This number should go here. So you should repeat it for all the numbers in those 6 individual 4 by 4 matrices and put all of them into the right places in the bigger 8 by 8 matrix. So if any cell receives more than one numbers in this process, you just add them together and with respecting to the signs. If any of the cells didn't get any input, like you see here, 0, or this 0 can be a result of getting 2 inputs, but in a different, with the different signs. For example, one input comes from somewhere zero point 0.1 and another comes from another way minus 0.1. So the result will be 0. Doesn't matter if you didn't get any input for any cell, it's 0, or if you get a couple of inputs in which the resultant of those will be 0, again it's 0. Anything you will get, just respect, and but just keep in your mind that you need to put all the elements into the bigger matrix and not to miss any of them. So again, I recommend you to use a kind of, I don't know, marking, like um, um, make a star with pencil beside each number, and that means that you have already implemented it in the bigger matrix, just to be sure that all the numbers have a very small star beside them, and use these kind of tricks just to be sure that all the numbers already have gone through the different cells in the bigger matrix. So this is after this, we have the 8 by 8 bigger matrix for the whole structure. And do not try to inverse this matrix because it's irreversible and the determinant might be 0 or negative, because so far we haven't done anything regarding the supports. So it doesn't understand this structure have any support. So we need to apply the boundary conditions for this 8 by 8 matrix. For this purpose, before proceeding, for this purpose, we know that three of the degrees of freedoms are correspond to the support deformations which are 0. If you take a look at the structure, you will see that 7, 8, and 6 are uh, the degrees of freedoms are 0. The displacements are 0 because they are support. So the bottom support is a roller one, which can move along the y direction, but the top support cannot move at all. So 6, 7, 8 are 0. So if you take a look at here, this is the stiffness matrix, 8 by 8, 6, 7, 8 are 0. And as I said before, wherever your support reaction, where you have a support, which means that the deformation are 0, on the other side of your equations, you have support reactions. Q6, 7, 8 are support reactions. And D1 to D5 are D1 to D5 are deformations in degrees of freedom 1 to 5, which are unknowns. We need to calculate them. And always when we have some unknowns like this, in the left-hand side of the equation, we have external forces which are known, right? So we want to solve this structure for two external forces applied in node number 4. Uh, yes, node number 4, which are, as you see, 4 kilonewton and 2 kilonewton. So remember that this is X coordination system and this is Y coordination system. So just respect to the coordination system, F1 and F2 are 0 because they are corresponding to degrees of freedom 1 and 2. Just take a look. Those forces are applied to degrees of freedom 3 and 4. See, 3 and 4. 3 is in the x direction, 4 is in the y direction. That's why 2 kilonewton sits in the third place. This minus 4 sits in the fourth place because these two forces are applied in the degrees of freedoms 3 and 4, right? And why this is minus 4? Because the 4 kilonewton is applied in the uh, opposite way of the y coordination system. It's in the upside down. So the definition of the coordination system is like x and y. So if this 4 kilonewton was uh, uh, reverse, I mean the arrow was downside up, it should be plus 4 kilonewton. And the fifth number is 0 because the fifth um, coordination degrees of freedom is here. We don't have any forces there. We could have, if you had some forces like, for example, if you could have some forces here, you put it in the fifth place here. But for now, we don't have any. So with this approach, you have this important equation. Again, I recall you, it's exactly like F equal to K multiplied by delta. Delta and F are two vectors. Delta is the vector of displacements, and F is the vector of external forces. The support reactions are kind of external forces as well. And the between matrix is the K matrix, which for the whole structure, the 8 by 8 matrix. So F and delta are the vectors 8 by 1, and the K matrix is a matrix 8 by 8. Uh, we need to apply the boundary conditions, and for that purpose, we just take a look at the delta, uh, which are equal to 0. So we see that we have 3 zeros here in the row number 6, 7, and 8. For example, for the 6, just eliminate row number 6 and column number 6. For the 7, for this 0, eliminate row number 7 and column number 7. For the 8, just eliminate row number 8 and column number 8. And what will remain for you is a kind of 5 known numbers here, 5 unknowns here, and a 5 by 5 matrix here. So we just rewrite the remaining parts of the problem here. This is the external forces. This is the remaining 5 by 5 matrix remaining from that 8 by 8 whole matrix. And this is the unknown displacements. Now, when you come up to this stage, you can reverse the matrix. So you can say if F is equal to K delta, the delta would be the inverse of this 5 by 5 matrix multiplied by this 5 by 1 external forces. If you do that, I strongly recommend here just to go to my recorded video about how to inverse the matrix by Excel or MATLAB. And it's really easy to do it with Excel, just to inverse this and multiply it by the vector of external forces. If you do that, you will come up with the delta 1, 2, 3, 4, 5, which are the deformations in different degrees of freedoms 1, 2, 3, 4, 5. And um, uh, with this stage, you can say you have already solved the problem in terms of deformations. That's all. And however, still you can go to um, calculate the support reactions as well as internal forces. For the support reactions, as you know, we use those rows and columns that we already eliminated. For example, Q6 is this line multiplied by this 8 by 1 matrix vector. So you can just write that one. Q6, Q7, and Q8 are really, it's like I'm writing these three are this part of the matrix multiplied by this part plus this part of the matrix multiplied by these 0, 0, 0, which is not important. So the second part, this part is here, which is 0, 0, 0. And forget about this. And Q6, 7, 8 is just really this part multiplied by this. But if this is difficult for you, just go and write this 6 row of this big matrix. Say the Q6 is this 6 line times this column. So it will be Q6, this one multiplied by this one, and you will get minus 4 kilonewton. And the same thing for Q7 and Q8. So basically, sorry, basically we use those eliminated lines that belonged to the boundary condition or supports, and with those we can get the support reactions, right? And the only thing remaining, the last one, not the least, is the internal forces for each element. Again, I recall you that the internal forces for each element is coming from this simple equation. For the far end of each element, you only need AEL and lambda x and lambda y, and all the deformations in the near end and far end of each element. For example, just let's do ones of them together. Q2, for example, Q2 is the internal force, which is either tension or compression, axial force in element number 2. So if you take a look at here, element number 2 is connecting node number 1 to 3. I know lambda x, lambda y are here, so this is minus lambda x, minus lambda y, lambda x and lambda y, okay? And these two are the deformations in the near end, which is node number 1, which is delta 1 and delta 2. So we need to put these two here, as you see. These two go here. And the remaining, these two are the deformation for the far end, which in the case of element number 2, the far end is joint number 3, which corresponds to degrees of freedom 7 and 8. And we know that the 7 and 8, this deformations in degrees of freedom 7 and 8 are 0 because they are support. So we just put 0, 0. They are really 7 and 8 are these two. See, they are 0. So if you multiply this 1 by 4 vector by this vector, which is 4 by 1, the result will be a scalar value, scalar number, which is 2.56 kilonewton. You can repeat it for every single element. We don't have the results for the other elements here, but you can do it, repeat it for all the elements to get the internal forces for each element. And another thing is that you can do a control point for your calculations by verifying the equilibrium equations. For that purpose, you already have the support reactions. You have this support reaction and these two, and you have two external forces. So as you see, the support reaction is -4. For example, here is -4. I'm just using these three numbers. Q7 is here 2, and Q8 is 4 kilonewton. So you have these three support reactions and these two external forces, free diagram of the whole structure should be in equilibrium. So you can say summation of fx should be 0, which is already 0. We have 2 minus 4, 0. And the equilibrium of Fy should be 0. You have two forces, 4 and minus 4. And you can also verify that summation of m is equal to 0 against any arbitrary point. This gives you a kind of reassurance that your numerical calculation is correct and flawless. And we are really at the end of this example as well. Before we proceed to the next one, if any question in any part, just raise your hand, please. Okay, good. Either everyone understood everything or nothing at all. There is not any other case. So let's move to, I think this is, yeah, this is the last example for today. This is another truss structure comprising with 3 elements. Again, this is indeterminate. Obviously, we have 3 simple supports, altogether 6 reactions. This is, sorry, I need my pen. This is the coordination system, X and Y, right? Again, you can change the coordination system to see how does it work. And after defining the coordination system, you can number the joints. As you see, we have 4 joints. We numbered 1, 2, 3, 4. And we have 3 elements. So we have element number 1, 2, 3. And we have altogether 4 joints, each joint 2 degrees of freedoms, which means 8 degrees of freedoms again. And we can number the degrees of freedoms as well by like degrees of freedom 1, 2, 3, 4, 5, 6, 7, 8. And with numbering the nodes, elements, and degrees of freedoms, we can jump into the assemblage of the whole stiffness matrix. Somehow this example is somehow similar to the previous example because it has 8 degrees of freedoms, but less elements. So more supports. So somehow you have less thing to do in terms of calculations. But the difference is that, well, for this structure, we don't have any external forces, and we have a kind of settlement downward equal to 25 millimeter in joint 1. In this joint, the whole support goes down 25 millimeter because of some reasons. The reason can be like this support is a kind of support in the middle of a river, and after a few years of river washes up some surroundings of the support will get some settlements, or any other reasons. It means that the ground underneath the support has moved somehow downwards. It's an effect that you can see in some real structures as well. So uh, we want to see how does it work in the context of direct stiffness methods. And to be honest, every single effect like this one is very straightforward to be implemented in the uh, direct stiffness method or matrix analysis. Uh, and this is not really straightforward in the force-based approaches, as you know. For the first force-based approaches, rather than the virtual work method, which was quite strong to implement different kind of these kind of effects. Other approaches we were through were not very strong enough to be able and capable of implementing these kind of effects. But this matrix analysis or direct stiffness method we are currently studying is very powerful of taking these kind of effects into the problem. So assembling the whole stiffness matrix is not very different from the previous example. You really need to assemble um, individual stiffness matrix for element number 1, 2, and 3 by calculating lambda x and lambda y for each one and putting them into the 4 by 4 matrix we spoke about here. We are just using this matrix again by calculating lambda x and lambda y just to come up with some sort of stiffness matrix for each individual element. So if you write these kind of 4 by 4 matrices, just bear in mind that for each individual 4 by 4 matrix, you need to write some hints on top of them, like for K1 comes from element number 1, which connects uh, node number 1 to node number 2 with this arrow, which means the near end is node number 1. So if it's node number 1, the degrees of freedom will be 3 and 4. And for node number 2, the degrees of freedoms are 1 and 2. And for example, for element number 2, this one, the near end is node number 3. Sorry, the element number 2, the arrow is this one. And the near end is node number 2, which means degrees of freedom 1 and 2. And the far end is node number 3 with degrees of freedom 5 and 6. And for element number 3, the near end is node number 4 with degrees of freedoms 7 and 8. And uh, the far end is node number 2 with degrees of freedom 1 and 2. So again, you need to put all of these 3 4 by 4 matrices into the bigger matrix, which is 8 by 8, obviously, because you have altogether 8 degrees of freedoms. If you put all them together, you will come up with this big matrix. Again, for this big matrix, you can write the famous relationship of if F equal to K multiplied by delta, delta D1 and D2 are free. They are free to move and they are corresponding to joint number 2 here. And as you know, wherever you have some free degrees of freedoms to move, on the other side of the equation, you have some external forces. In this case, you don't have any external forces. They are 0. Because the only effect in this example is the support settlement. However, if in any case, in any example, you had a kind of support settlement, and you had also some external forces on joint number two, it's fine just to put those kind of forces into these two places, and they will add up with the effect of the support settlements as well. So for the degrees of freedom 3 to 8, they are the um, in the F vector, they are unknown because they are support reactions. Q3, 4, 5, 6, 8, they are unknowns, support reactions. And on the other hand, these are all, usually they are zero because they are supports. But in this case, all of them are zero, but this one is 0.025 meter. We just transform 25 millimeter to meter to be consistent with the AEL, with the AE and L that we are using into the problem. So usually if we didn't have support settlement, this place would be zero, but this is not. The support settlement goes here, and this affects your calculations in a way that usually if we didn't have the support settlement, we would go for elimination of the rows and columns of 3, 4, 5, 6, 7, 8, because we had zero in the delta vector. But here we should be careful about that. And we need to write like this. We just it's just right really like multiplying this big matrix by this vector and just uh, decomposing from the a stiffness form to a couple of uh, group equations, like 8 equations. You can, when you have something like this, you can just decompose them into 8 single equations or vice versa. Like you can say, if you just take a look at my mouse cursor, um, just take another color like this one. I can say this one, which is 0, 0, it's here, is equal to this part of the matrix, multiplied by D1 and D2, plus this part of matrix, plus this part of the delta vector, which is this one. In the previous cases, this part, in the previous cases, this part was absolutely zero, and we didn't have this part because it was zero. And that's why, for example, in the previous cases, the author of the book was used to write this part, which was 0, 0, 0, and it doesn't influence anything. But he insisted to write this part intentionally to say that this is here, but it is zero. But when we have some support settlements, it is here, but it can be non-zero. So the support settlement is here. And if you multiply this, see, it is 2 by 6, and this is 6 by 1. So the resulting product will be 2 by 1. So it's 2 by 1. It's like if you multiply these two together, you will come up with a 2 by 1 known vector. And if you bring it in the left-hand side of the equation, it will be added to this current 2 by 1, 0, 0 vector. And it's like that this support settlement is kind of transforming to an equivalent external forces coming to the left-hand side of the equation. And this part is still there to be solved for D1 and D2. So the support settlement is just some known that contribute to the solution of the problem by modifying the external forces vector. If you go and solve this equation, again, you can see that you will have two separate equations here. And if you solve it, you will come up with D1 and D2 as the deformations in the degrees of freedoms 1 and 2. And the rest of the problem is really the same as before, because the only difference here is how to implement that kind of support settlement. But when you got the D1 and D2, you can just go and use these kind of Q3 to Q8 to get the support reactions. Just to be careful, you have this number here, and you can use the simple formula like this to get the internal forces for each element, as there is only one case for element number 2, and the rest of the problem is the same as before. Uh, any question for this slide? Um, so far, we have covered the truss structures. We have one last slide, but I just passed this slide because it's about if we have some inclined support kind of configuration. And this is not something that I'm going to teach you. It's just the last page of the book, and just put it here. Just skip this last slide, and this is not going to be questioned in the exam. So the only effect that we went through is the effect of support settlement, as you see. So you can have some external forces on different joints, or a kind of support settlement like this. Otherwise, we just skip the other effects that. But you should know that there are different techniques that can implement different kind of effects into consideration. For example, if you have if you're warming up some element, or cooling down some element, or if you have some distributed forces rather than concentrated forces on joints, distributed forces on elements, or you have some imperfection in terms of the lengths of the element. There are different kinds of effects that this approach is able to take into consideration. The only effect that we went through is actually two effects. The concentrated loads on different joints is one kind of loading the structure, and the support settlement is another kind of effect that we went through, how we can solve the structure based on these kind of effects. For the next session, we will go through the same concepts for the beams, and after that for the frame structures. However, the procedure that we were following in the truss structures will be stay there the same, like defining the coordination system, numbering joint, numbering elements, numbering degrees of freedoms, then assembling the individual stiffness matrix for different elements, then putting all of those individual stiffness matrices together to get the bigger matrix for the whole structure, then apply the boundary conditions to come up with a smaller uh, stiffness matrix for the structure with only the unknown deformations. Then we get the unknown deformations by solving the equation F equal to K delta. And then when we get the unknown deformations, we can go to calculate the support reactions by using those eliminated lines and columns. And then we can go to calculate the internal forces in each element. This is the whole story that we were through in for different truss structures, but the algorithm and the sequences will be exactly the same for the beams and frame structures. Uh, so we are done with the truss structures, and we have to leave the beam structures and frame structures for the next semester. And I will let you know by an email about the influence of this on your coursework as well in a few days. And so you can assume that all the things about direct stiffness method for beams uh, will be moved to the next part of the coursework in the second semester. Um, any question? So if there is not any question, um, before wrapping up the meeting, I wish you all the best time for the festive period, the Christmas and the New Year, and I hope you will enjoy your time, and see you all in the new year. Have a nice rest of the day, and goodbye. Ah, still good, good. Somebody spoke something. Uh, no, for today, there is no need for recording any attendance because it was online. It's not gonna be accounted in the proportion of the attendance. Don't worry about that. Uh, you don't need to record it for today. The lecture is recorded, and I will put it in the Moodle after we finish up. But you don't need to record any attendance for today. Any other question, comment? So if there is not any further comments, again, I wish you all the best for the Christmas and the New Year, and see you all freshly in the new year to learn more about engineering analysis and applications. Good luck and have a nice rest of the day. Bye bye.